All right, so the second of these review problems is a little bit more mathematically involved. So as we'll see, parts A, B, and C are ones that you should be able to do pretty straightforwardly using what we've learned. Parts D and E are a little bit tougher, but they're a good challenge, and you should be able to at least set them up and understand the process. All right, so let's start. The first thing is that we're starting with a block that's a little bit above a vertical spring, and then we drop it from rest. So we want to know how fast it's going right when it hits the spring. And there's two different ways you can do this. You can either use energy conservation, you're converting gravitational potential energy to kinetic, or you can use kinematics, right? The force that pulls the block down is gravity, so you can get the acceleration, and then from the acceleration and the distance traveled, you can get the speed it has at the end. I'm going to do it with the energy conservation way because that is a little bit faster. Either way would work. So, energy is conserved, right? We're ignoring air resistance. And so we're converting gravitational potential energy, mgh, into kinetic energy, 1/2 mv squared. We know how far it falls, it's 0.45 meters, and we know the mass, not that it actually matters because it cancels, and we know g. So we can multiply by 2 and take the square root, and we get that v is the square root of 2gh, or the square root of 2 times 9.8 times 0.45. Right? And you plug all those numbers in, and you will get that the block is traveling at 3.0 meters per second when it hits the spring. So that's part A. Part B. We need to know the period of the simple harmonic motion that starts. And we know what the period is for springs, 2 pi square root of m over k. And we know all these values. Right? We're given the spring constant, and we're given m. So plug it in. 2 pi square root of m is 2 kilograms. K is 200 newtons per meter. And if we plug all that in, we're going to get a period of 0.63 seconds. Again, fairly straightforward. Identify the equation and put the numbers from the problem right in. So part C is a little bit trickier because you have to do some thinking about what math you're going to do. And so we're told we want to know the distance the spring is compressed at the instant the speed is a maximum. And we know from our simple harmonic motion discussion, the speed of the block is the maximum when the block is in equilibrium, right? When there's no net force on it. So, right, our block has, as it's falling downward, a spring force up and a weight down. And when there's no net force, right, the net force is 0, or those two are equal magnitude opposite direction, that is, actually I should clarify, this is ky, but when those two forces are equal, that tells you when it's at equilibrium. When it's at equilibrium, the speed is a maximum, and so we can figure out the compression amount at that point. Right? So k times how much it's compressed to be at equilibrium minus mg equals 0. So we find that the compression amount at equilibrium is mg over k. And again, we know all these numbers. It's 2 times 9.8 over 200. And so that tells us that the amount the spring is compressed when the speed of the block is a maximum is 0.1 meters. So that part is tricky if you don't remember that definition of equilibrium. If you don't remember that definition of what equilibrium is, the speed is a maximum there, then you have to do some very complicated math that we haven't really covered. It takes a little bit of calculus. So remembering that definition turns the problem into a very easy equation to solve using sort of free body diagram information. All right, parts D and E are a little bit trickier, but you should definitely be able to set them up. And the math, assuming you have a graphing calculator with you, is not too bad either. So we want to know the maximum compression of the spring. So we drop the block on it, it goes down, it's at a maximum speed equilibrium, and it keeps going down until eventually the spring brings it to a rest and starts pushing it back up. So let's kind of just do that drawing, right? We're going to talk about this in terms of energy conservation, because the maximum compression of the spring happens when the block comes to rest, right? That's another thing we know from our discussion on simple harmonic motion, is maximum compression is when all the energy is in potential, none of it is in kinetic. So our sort of before and after picture is going to be something like this. So initially, right, it just hits the spring, and then after, it has compressed it a lot, right? And so this is like the before. So here, V equals whatever we found in part A, the 3.0 meters per second. And here, V equals 0. That's the definition of maximum compression. And so what we're really trying to find is sort of this distance right here, right? How much the block goes down from the uncompressed spring to the maximum compression before it comes to rest. And so as you can see, this is an energy conservation statement. So we'll call this height y equals 0. So right up here, we're at y equals whatever that delta y is, right? The amount of compression that we do. So now we just need to write the energy before and energy after and set it up. So before, we have two types of energies, right? It's both moving and it's above our minimum. So, right, energy is conserved. Before, we have mg delta y, right? That's our potential energy, plus 1/2 mv squared, because it's moving as well. And after, we only have spring potential energy, given by how much the spring is compressed, which is that delta y again, right? And the spring potential energy is 1/2 k delta y squared. So if you can just set this up right here, that's good, right? That's just recognizing physics stuff. Now, as you can see, since we're going to solve for a delta y equals thing, we have a quadratic equation. So it's a little bit more mathematically involved, but calculators are good at that. But this part is the physics. Now we just need to do the math. Right, so if we rearrange, we can get delta y squared minus 2mg over k delta y minus mv squared over k equals 0. Right, and this is a quadratic equation in terms of this delta y. So you plug that into the quadratic formula with, right, so, right, I'll just kind of write it. I'm not going to write the whole thing out. But we need coefficients, right? Here, A, the coefficient on the squared term is 1. B, the coefficient on the linear term is negative 2mg over k. And we know all those values, right? We can calculate that. And C, the coefficient on the term that doesn't involve any delta y, is negative mv squared over k. And again, we know all those values. So you plug all those into the quadratic formula, and you'll get an answer that delta y equals 0.41 meters. And again, the setup is the important part. If you can sort of get to this point, then you're in a good place. That's the physics. The rest is math. It's good practice, but you have to be able to sort of recognize that how the energy sort of moves around in the system. All right, so that's part D. Part E is somewhat tricky, but it's, if you can recognize what the definition of amplitude is, you can see how to get the information from parts you've already done. So the definition of amplitude is the maximum displacement from equilibrium. And so we found the equilibrium position in part C, right? How much the spring was down when the block was moving its maximum speed. That was 0.1 meters. And we found the maximum compression in part D. That's the 0.41 meters, right? That's part C, that's part D. And so even if you can't do part C and D, just recognizing that what part C is telling you is the equilibrium position, and part D is telling you the maximum compression, and part E is asking you about the maximum distance you travel from equilibrium, should let you, again, conceptually set up what part E is asking, which is really what's the difference between these numbers. So the amplitude is 0.41 meters minus 0.1 meters, or 0.31 meters, right? Because if your equilibrium is 0.1 meters down, and your maximum compression is 0.41 meters down, then you travel a total of 0.31 meters away from that equilibrium point in your oscillations. So again, if you get to that point and recognize what you're trying to do, but don't have the numbers, make up a number for part C, make up a number for part D, subtract them, and explain why in part E. And you'll get the points for that. So again, just to reiterate, parts A, B, and C are ones that you absolutely should be able to do. Parts D and E are challenges for an AP Physics 1 class. This is a Physics C question. And if you can sort of set them up, then you're kind of in a good spot. And being able to do them is a really good sign for the test. It means you'll be very ready.